Today's topic is absolute potential energy. Now we are going to calculate absolute potential energy. Consider a body of mass m situated at some point. If it is raised through a vertical height h at a constant speed which is small enough that it acquires no appreciable kinetic energy, the force required to raise the body is just equal and opposite to the weight, that is W is equals to mg. The work done in raising the body is W, force into distance, that is equals to mg h. Here force is mg, weight of the body, and h is height. The potential energy of a body at a height h from the earth is given by potential energy is equals to mgh. But now we have to calculate absolute potential energy. We know the formula of potential energy, that is equals to mgh. We know the potential energy. But now we have to calculate absolute potential energy, and we will move an object from the Earth's surface at the point infinity where the force of gravity is zero or very less, and their potential energy will be zero. For finding the absolute value of potential energy, we have to fix a 0 point for the potential energy. The 0 point for potential energy is a point so far away from Earth that is no longer influenced by the Earth's attraction. Hence, its potential energy is zero. So, for finding absolute value of potential energy, we just put an object from Earth's surface to the point infinity. That point is known as 0 point away from Earth's surface, where the force of gravity and Earth's attraction is zero or very less, and there the potential energy is zero. For finding the absolute potential energy, we move the object m from Earth's surface, from this point Earth's surface, to point 1, and we move this object from point 1 to point 2, from point 2 to point 3, and up to point n, and point n is at infinity where the force of gravity is zero, where the attraction of Earth is zero or very less, and where the potential energy is zero. So we move object from Earth's surface to point infinity, very far away from Earth's surface. A body of mass m is placed at point 1 at distance r1 from center of Earth of mass me and radius re. Mass of Earth is me, radius of Earth is re, and we put mass from surface of Earth to point 1. Here mass m, object having mass m, is placed at point 1, and distance from Earth's center to point 1 is represented by r1. We want to displace this body from point 1 up to point n. So actually we want to do some work done on this body to displace it from point 1 up to point n. We have divided the whole distance into a number of small distances, each of magnitude delta r as shown in figure. Because we move this object far away from our surface, so force of gravity does not remain constant. To make the force constant, we divide this distance into number of small distances, and they are represented by delta r, because the difference between point 2 and point 1 is delta r, that is equals to r2 minus r1, and difference between point 3 and point 2 is r3 minus r2, and similarly difference between point 4 and point 3 is delta r is equals to r4 minus r3. Similarly, difference between point n and point n minus 1 is Rn minus R sub n minus 1. So point 1 is from center of Earth to this point, and that is represented by R1, and point 2 is from center of Earth to this point, that is represented by R2. Point 3 is from center of Earth to this point, that is represented by R3, and so on. It is assumed that the force during each interval remains constant, because now we had divided the whole distance into n number of small distances. So for small distances, force is constant. Work done between point 1 and point 2 will be, because now we are displacing this object from point 1 to point 2, so we do some work on this object. So we do some work on this object from point 1 to point 2 for moving it from point 1 to point 2, and that work done is delta W from point 1 to point 2. Delta W sub 1 to 2, point 1 to 2 is equals to force into displacement. So force is here average force into displacement. Displacement, we know that difference between this point R2 and point R1 is delta R. So delta R is the displacement from point 1 to point 2, and delta R is equals to R2 minus R1, this displacement minus this displacement. So R2 minus R1 gives us this displacement delta R between point 1 and point 2. So delta R is equal to R2 minus R1. Let's say it equation number 1. And we know that F is equal to G small m, that is mass of this object, into capital M sub E, that is mass of Earth, divided by R average square. Here R average is equals to R1 plus R2 divided by 2. Now we put the value of F average in equation number 1, and we get work done from point 1 to 2 is equals to G small m capital M sub E divided by R average square into R2 minus R1. Let's say it equation number 2. We know that small displacement delta R for point 1 to 2 is equals to R2 minus R1, and from here we get the value of R2 by shifting minus R1 on left hand side of the equation. So R2 is equals to delta R plus R1. Putting the value of R2 in equation, R average is equals to R1 plus R2 divided by 2. We get R average is equals to R1 plus delta R plus R1, that is the value of R2 divided by 2. R1 plus R1 is equals to 2R1, and now we can divide numerator separately with denominator, and we get R average is equals to 2R1 divided by 2 plus delta R divided by 2. 2 is cancelled with 2, and we get R average is equals to R1 plus delta R divided by 2. By squaring this equation on both sides, we get R average square is equals to R1 plus delta R divided by 2 whole square, and R average square is equals to, now applying the formula A plus B whole square, that is equals to A square plus 2AB plus B square. We get R1 square plus 2 into R1 delta R divided by 2 plus delta R divided by 2 whole square. Delta R is very small, so we neglect it, and we get R average square is equals to R1 square plus 2 is cancelled with 2. So we get R1 delta R, R1 into delta R, and this term is neglected. R average square is equals to R1 square plus R1. We put the value of delta R, that is equals to R2 minus R1. And now we can multiply R1 with the term in brackets, and we get R average square is equals to R1 square plus R1 into R2, plus minus is minus, and we get R1 into R1, that is R1 square. R1 square is cancelled with minus R1 square, and we get the value of R average square, that is equals to R1 into R2. Now we can put the value of R average square in this equation number 2 here. So work done from point 1 to 2 is equals to GMME divided by R1 into R2, that is the value of R average square we calculated in previous slide, into R2 minus R1. When we divide denominator with numerator separately, R2 is cancelled with R2 and we get 1 upon R1, and minus R1 is cancelled with R1 and we get here 1 upon R2. So similarly, work done from point 2 to 3 is equal to G small m capital ME into 1 upon R2 minus 1 upon R3. Similarly, work done from point 3 to 4 is equals to G small m capital M sub E into 1 upon R3 minus 1 upon R4. Similarly, work done from point n minus 2 to point n minus 1 is equals to G m capital M sub E into 1 upon R n minus 2 minus 1 upon R n minus 1. Similarly, work done from point n minus 1 to point n is equal to G small m capital M sub E into 1 upon R sub n minus 1 minus 1 upon R n. We can calculate work done from point 1 up to point n by summing up all the work done that we calculated in previous slide. Work done from point 1 to 2 plus work done from point 2 to 3 plus work done from point 3 to 4, so on up to plus work done from point n minus 2 to n minus 1 plus work done from point n minus 1 to n. And by putting all the values of work done, we get this equation. In this equation, one term is same in all the terms, that is G small m capital M sub E. So we can take it as common from all the terms and we get work done from point 1 to n is equals to G M M E into 1 upon R1 minus 1 upon R2, plus this term is taken as common, so we get 1 upon R2 minus 1 upon R3, plus this term is taken as common, so we get 1 upon R3 minus 1 upon R4, plus so on, plus this term is taken as common, so we get 1 upon Rn minus 2 minus 1 upon Rn minus 1, plus this term is taken as common, so we get 1 upon R sub n minus 1 minus 1 upon R sub n. Terms in between 1 upon R1 minus 1 upon Rn are all cancelled by each other. Minus 1 upon R2 is cancelled with plus 1 upon R2, minus 1 upon R3 is cancelled with plus 1 upon R3, and so on. And here minus 1 upon R n minus 1 plus 1 divided by R n minus 1 is cancelled with each other. So finally we get this term 1 upon R1 and this term 1 upon R minus 1 upon Rn. So we get work done from point 1 up to point n is equals to G small m capital M E into 1 upon R1 minus 1 upon Rn. Let's say it equation number 3. Because Rn is the point at infinity that we have taken at infinity, so we moved that object having mass m from point 1 up to point n, and that is infinity point. So we put Rn as R infinity. So 1 upon infinity is 0, and we get work done from point 1 to point infinity is equals to G small m capital M sub E into 1 upon R1 minus 0. So finally we get the term work done from point 1 to point infinity is equals to G small m capital M sub E divided by R1. This is 1 to infinity, from point 1 to infinity, work done from point 1 to infinity. It's not minus sign, it's 1 to point infinity, 1 to point n. Okay, so we have work done from point 1 to infinity is equals to Gm capital Me divided by R1. Let's say it equation number 4. If we displace the body from the surface of Earth of radius Re, then we replace R1 by Re, and equation 4 becomes work done from point 1 to infinity is equal to G M Me divided by Re. We just write Re instead of R1 because we move the body from the surface of Earth, and from there the distance from center to the surface of Earth is radius of Earth, and that is represented by RE. So we can write R1 is equals to RE. From the surface of Earth up to infinity, absolute potential energy is equals to GMME divided by RE. It is the work done against gravity, so its value is always taken as negative because we are moving object from surface of Earth up to point infinity. So we are doing work done on the body against the gravity. So there must be a negative sign. So absolute potential energy is equals to minus G MME divided by RE. Now we can define the gravitational potential energy at any point. The amount of work done in moving a body at a certain point in a gravitational field to a position of zero potential such that the body is never accelerated is called absolute potential energy. Now you have clear idea about absolute potential energy. We do some work done on object in gravitational field at certain point from the surface of Earth, and we move that object at position of zero potential far away from Earth's gravitational field, and that body is not accelerated, and that is called absolute potential energy. Now gravitational potential energy, gravitational potential, we have discussed gravitational potential energy. Now what is gravitational potential? Okay, don't be confused with the both terms. We have discussed gravitational potential energy here, and now we are going to discuss gravitational potential. Now gravitational potential at any point is defined as the potential energy per unit mass at that point, which is at distance r from the center of Earth, and is given by gravitational potential represented by V sub r is equals to minus G capital ME divided by RE, because it is the potential energy per unit mass. So potential energy, absolute potential energy is divided by mass, so M is cancelled with M, and we get gravitational potential is equals to minus G capital M sub E divided by RE.